Hello, so in this video I will be going through all of the questions from Unit 1 in the midterm review packet. So if you had questions on any of them, this would be questions 1 through 9. Please listen in, follow along, and hopefully this helps. So we'll go in order. Starting with question 1. So question 1 asks about whether something is a physical or a chemical change. So the difference between physical and chemical, remember, a chemical change creates something new. So the reason that they're creating something new is because we really have a chemical reaction happening. Okay, so we're combining different reactants to make a new product. A physical change is more of a surface level change. So there is a change happening, but it's not changing the identity of the substance. In other words, nothing new is produced in a physical change. So when wax melts, it's still wax, it's just melted now. Any change of phase, so melting, freezing, boiling, anything like that will always be physical. Iron rusting, when something rusts, what you really have is you have the iron in the air reacting with the oxygen, the iron reacting with the oxygen in the air to form some sort of iron oxide. So that could be iron 1, that could be iron 2, there's different versions there. But the point is, this thing, the rust, is a new product. So that is a chemical change, it's a chemical reaction. 1C sounds like a chemical reaction, right? Hydrogen and oxygen combining together to form water. Water is the new product, so that is a chemical change. And distillation, so it tells you that's separation by boiling. So since we're just boiling things away, that's a change of state, but that is still just a physical change. Okay, the two substances would still be the same things, they just would be separated now. So there's our physical versus chemical. In question 2 is asking whether something is a physical or a chemical property. It's the same principle, so still ask yourself, would that principle result in something new being formed or not? Okay, so something's color has nothing to do with something new being formed. It's just a property that is sort of set for every substance. So that's a physical property. The fact that anything can react with oxygen, if it's reacting, that's a chemical change. So that means that would be a chemical property, reactivity with oxygen. Whether something is soluble in water. I know dissolving sounds like a chemical process, but whenever you dissolve something, you're really just taking, if it's a solid, you're really just going from a solid to an aqueous state, but it is still the same thing. So anytime you're talking about dissolving or something being soluble in something else, that's a physical property. Density, remember, is mass over volume. But the fact that something has a specified density has nothing to do with creating something new. It's just, again, a designated fact for every substance. So density is a physical property. And then last but not least, whether something is an acid or a base. Acids and bases, by definition, react with other things in neutralization reactions. So since we're talking about a neutralization reaction, something new would be produced. Remember, the reaction of an acid and a base always produces water and a salt, which is just an ionic compound. So something new would be formed that would make 2E a chemical property. All right? So let's move on to the next questions now. So the rest of the questions on that page, continuing along with Unit 1. Question 3 asks whether something is extensive or intensive. So the difference between those two. Intensive properties essentially don't change because they are independent of the amount of substance. Meaning, if you have a lot or a little bit of something, that property will still never change no matter what. Okay? Whereas an extensive property will change if you have more or less of something. So we could say it will change based on amount. So let's look at our examples. Volume. If you have more or less water in a cup, the volume of that water will change, which means that would be extensive. Something's boiling point is a fixed temperature. So for example, water always boils at 100 degrees Celsius. If I have a glass of water or a giant pasta pot filled with water, it will still boil at 100 degrees Celsius. So boiling point will never change. It's fixed, so it is intensive. It's independent of the amount. 3C, the mass. If I have more of something, it weighs more. If I have less of something, it weighs less. So mass is definitely extensive because the more or less I have of it, the more that mass will change. 3D, remember density is equal to mass over volume. Now what we have to remember is even though mass and volume are both extensive, the ratio of those two is always fixed for a specified substance. So for example, if you have one brick, it's very dense. If you have an entire brick wall, it's still just as dense. Yes, the mass of that wall would change, but the ratio of how close together the atoms and molecules are is fixed. So density is an intensive property. Every substance has its own density that does not change. So moving on to question 4. The difference between precision and accuracy. So you can look these two up in your notes, but the main difference is that precision deals with how close values are to one another, whereas accuracy deals with how close values are to the accepted value. So if you think of this in terms of a bullseye, let me just draw a dartboard here quickly. If your darts hit all in the center, all close together, that would be precise and accurate because they are close to where they should be, the bullseye, and they are close to each other. They are precise. If our darts looked like this, in purple there, those would not be accurate, nor would they be precise because they are not close to the center and they are not close to each other. We can have some of each. So if I have something that looked like this, these blue ones, these darts would be precise because they are close to each other, but they would not be accurate because they are not near the bullseye. So hopefully that helps distinguish between those two. And going along with that, percent error is a way to calculate how accurate your data really is. So the percent error formula is in your reference book. If you go to the back section where you have the equations and constants, you will see percent error the formula for percent error listed under the measurement heading. Okay, if we move on to question 6. So question 6, 7, 8, and 9, all we have to show some work for because all of these are math problems. So question 6 says a solid object with a mass of 22.5 grams and a density of 4.5 grams per mil is placed in a graduated cylinder with 30.6 milliliters of water in it. When the object is completely submerged, what will the new volume reading be? So if we're taking an object that we know the mass and density of and we're putting it into water, we're essentially trying to use the displacement method, okay? So the first thing, as soon as you see the word density, never a bad idea to jot down the formula that you need, all right? So there's our formula. If I now rearrange this, because what don't I have? I have a mass and I have a density. The only thing I didn't have is the volume. So if I rearrange this and solve for V, we would get that our volume equals the mass over the density, right? So if I plug in the numbers we had, even if you're not quite sure why, at the very least, if you have a formula and you have all but one variable, plug into it and see what happens. So if I plug those numbers in, I see that the volume of that object, based on its mass and its density, must have been 5 milliliters. So if we're thinking of displacement, if the graduated cylinder originally had a volume of water of 30.6 milliliters, if you have this object in there, and we know that that object has a volume of 5 milliliters, once you submerge that completely, if we take the original water level and then we add the 5 milliliters for our object, we would see that this graduated cylinder would now have a reading of 35.6 milliliters. So again, just an application of density for that problem. If we look at question 7 asks how many millimeters are there in 2.95 times 10 to the 6th kilometers. So all we're doing is a metric conversion. So remember our metric system, we have King Henry died, belly up, drinking chocolate milk, or however you choose to remember that. When I'm doing my metric conversions, we still want to use dimensional analysis for this. So if I start with the number in the problem, which is our 2.95 times 10 to the 6th kilometers, I can go from kilometers to millimeters in one step because they're both in the metric system. The question is, what is my relationship between these two? Now, depending on how you've learned this, there are a bunch of different ways to do this. So I'll show you 2. But again, there might be others depending on how you learned it originally. So the one way you could do it is by looking at our metric system that I sketched out in purple here. If we do it this way, we're trying to figure out how many of the smaller unit are in the larger unit. So the larger unit is the kilometer or kilometer. So I would say that 1 kilometer. And the question is, how many of these smaller millimeters are in that? So how can I figure that out? All 6 of the prefixes I have shown at the moment are all separated by 1 power of 10. So if I go 1, 2, 3, 4, 5, 6 spots over, that would be 10 to the 6th, or in other words, million. So that means there are 10 to the 6th millimeters in 1 kilometer. So if we do our math then and just do 2.95 times 10 to the 6th times 10 to the 6th and then divide that by 1, we would see that there are 2.95 times 10 to the 12th millimeters in that measurement in kilometers. Okay, so that's one way we could set it up. An additional way we could set this up, again, just another way of showing this, depending on how you learn this originally, is we would still start with the number in our problem, which was our 2.95 times 10 to the 6th kilometers. And if you remember your values of the metric prefixes, if I keep this sketch in purple, but I erase this stuff from the other way, you know that if we always make our base unit 1, our prefix values come out like this. As again, this is assuming our base is 1. So if I want to do this in one step, I could also do that by using my, using my prefixes. So I have that there are 10 to the negative third for a kilometer, and there are 10 to the third millimeter. Again, that's assuming we are basing our base unit on 1, which is perfectly fine to do. I have to arrange them this way so that the units cancel. And if we do that, we would still get that same answer, 2.95 times 10 to the 12th millimeters. So again, there are many ways to do metric conversions. Whichever way you want to do is fine. You just have to be able to do them. So moving on to question 8. So question 8, we're dealing with still dimensional analysis, but you see that it mentions cubic centimeters and cubic decameters. So remember, when you're dealing with cubed units, you either have to do the same conversion factor 3 times, or you can write that conversion factor once and cube it, but you have to remember to actually cube it when you do that, which sometimes trips people up. So if we start with our given value, that would be our 10.8 cubic decameters, or decameters would be cubic decameters would look like that. So again, we have options here. We can go from decameters to centimeters and do that conversion factor 3 times. This way is a little bit more foolproof in that you won't forget to actually cube the value, but you can see it is a little bit longer. So you could also do this. Write the conversion factor once, and then you'll just cube it. I'll show you both. I'll do both metric ways the way we did in the previous problem. Choose whichever you prefer. So if we get our scale back here in the corner, again, assuming our base is 1, we get that. So if I use the prefix base values, which I just wrote down there, we can fill in this last one. So the relationship between a decameter and a centimeter would be that deca would be 10 to the negative first, and centi would be 10 to the second. And that could be my conversion factor, and I would need to remember to cube this. So remember that cube applies both to the 10 to the second and to the 10 to the negative third. So you have to cube both of those values, okay? So we can do that. And if you plug this in correctly to your calculator, you should get 1.08 times 10 to the 10th cubic centimeters. And that will work just fine. You also, if you're worried about forgetting to do the actual cubing, and if you like doing your metric conversions by making the larger one, the larger prefix value 1 and the other one some positive power of 10, you can do that as well. So if we do it that way, centi is 1, 2, 3 spots away from a deca prefix. So 1 decameter would have 10 to the third centimeters. And we could fill that in 3 times. Again, if you do that, and remember to actually plug it into your calculator correctly, you should still get this same answer of 1.08 times 10 to the 10th cubic centimeters. Okay? So there we are. And the last problem of this section, moving to question 9. So question 9 says the density, and it gives us this density in grams per cubic centimeter. And it's asking you to change that from grams per cubic centimeter to pounds per cubic foot. And it gives you a couple different conversion factors. So we need to do some dimensional analysis here. So first step, let's write our starting value, 2.68 grams per cubic centimeter. All right, so this is a derived unit, meaning I need to change both the top and the bottom. So you can start with whichever one you want. I'll start with the top just because it's the easier one of the two since we have this conversion factor right there. I have to put the gram portion in the bottom because I need the units to cancel. So when I do that, the grams would cancel out, leaving me with pounds up top, which is halfway where I want to be. But I also need to change my cubic centimeters to cubic feet. So how can I do this? Well, we know that there are 2.54 centimeters in an inch, and we know that there are 12 inches in a foot. So if I can go from centimeters to inches to feet, we can also go from cubic centimeters to cubic inches to cubic feet. So the same conversion factors. Again, you're either writing them all 3 times or you're writing it once and remembering to actually cube that and the values when you plug them in. So if I do it that way, just for space's sake for this one, I would put my 2.54 centimeters in the top and the 1 inch in the bottom. I have to do it that way so that the centimeters here, cubic centimeters here and here would cancel. And this would get us cubic inches at this point. So I would also need to do that there are 12 inches in 1 foot and cube that whole thing. So if you're worried about forgetting to actually cube this, you can also write this conversion factor once, but actually substitute the values. So what I mean by that is under this first one, it would be equally correct. If you do 2.54 cubed, that comes out to about 16.387. So that's how many cubic centimeters, 1 cubed is still 1, are in 1 cubic inch. So you could do it that way if you would like. And then for this second one, if you want to do the same thing for this one, again, 1 cubed in the denominator is still 1. Where you run into trouble is when there's not a number that's 1 in the denominator. Then you have to actually remember to cube it. But 12 cubed would be 1728. So what I have in blue could equally substitute for what I had in purple there. No matter how you plug this into your calculator, you should get that your answer at the end would be to 3 significant figures, because this has 3 significant figures, your starting value, 167 pounds per cubic foot. So those are all the questions in the review packet from Unit 1. The next video will cover all the questions from Unit 2.